but I've been active in science and critical thinking outreach pretty much since I left school. I've also done some writing on the topic of rationality and actually on evolutionary biology. And my opening presentation, thank you everyone for coming. Glad to see everyone here. My presentation is on Bayesian reasoning for skeptics, and I'm wondering how many people have heard of Bayesian reasoning before? Some of my friends know because they will not be allowed out of the room until they've had a personal private lecture from me. So the outline here, this presentation was inspired by my experience at SciCon in 2022. So SciCon, the big Skeptics conference, it was in Las Vegas. And I sort of informally polled the people that I was speaking to there, having conversations with, about whether they knew of Bayesian reasoning and what they thought of it. And of about 15 people I had conversations with, only 2 people had heard of Bayesian reasoning, and of those, they didn't like it. And they say they didn't really understand it very well, and I think I know why they had that point of view. But I think that Bayesian reasoning is very important in skepticism and in critical thinking. And I think that the way historically skepticism and critical thinking have been approached is missing something. And I'm going to try and explain what that is. It's sort of Bayesian rationality is the idea. And after I explain what Bayesian reasoning is, I'm going to apply it to the paranormal, so you can see like how it fits in. And I'm also going to talk about the misuse of Bayesian arguments, and I think that's where some people's skepticism about Bayesian reasoning has come from. So what is skepticism? It's kind of a good question to start a skeptics event with. I think it's not a specific set of conclusions. Like it's not the idea that ghosts, aliens, ESP, and magical cures do not exist, because if we did experiments and it was proven that they existed, then we'd be like, oh, okay, yeah, it exists. It's really a way of thinking, and the question is, what is that way of thinking? And I think that it's partly a vibe. It's kind of an ideology, and it's inspired by our leader, Carl Sagan, who's quoted as saying, "Ask courageous questions. Do not be satisfied with superficial answers. Be open to wonder, and at the same time subject all claims to knowledge, without exception, to intense skeptical scrutiny. Be aware of human fallibility. Cherish your species and your planet." Beautiful. But the line that I've highlighted there is intense skeptical scrutiny, and the question is, what is that? And I think, in my experience, for most skeptics, it's the application of certain aphorisms, things like, extraordinary claims require extraordinary evidence. Occam's razor, among competing explanations with equal predictive power, the one requiring the fewest assumptions should be preferred. A good theory should be falsifiable, and we should avoid logical fallacies. But I think there's a problem here, which is that those aphorisms do not constitute a full epistemology. Epistemology is a word in philosophy, meaning it's like a theory of knowledge, right? It's sort of the aphorisms by themselves are just piecemeal, like heuristics, right? But the question is, what is the underlying theory? If there is a theory, if there even is a theory, what is the theory that underlies all of this? And an example of where it gets maybe vague and imprecise is, what exactly is an extraordinary claim? And what is extraordinary evidence? Another quote I found from Carl Sagan is, absence of evidence is not evidence of absence. But sometimes it is, right? So a lot of these aphorisms seem to have exceptions to them, or they have nuance. And I think that what we would all do is we would look at that nuance and we'd sort of try and dive in and pick it apart. The other problem I see in critical thinking is that the way it's normally taught is we teach people how not to think, right? We say, don't engage with these logical fallacies, beware of your cognitive biases, ways that humans predictably deviate from rational thinking. So it's like, we're teaching people how not to think. But why don't we teach people how to think? What if there was a method or a formula that told us how you ought to think, right? What would an ideal reasoning machine do? What we need is a coherent epistemology, a theory of skeptical knowledge and scientific inquiry, a theory of epistemic rationality that tells us what we ought to believe true given the evidence. And a good candidate for this is Bayesian epistemology. Where does the word Bayesian come from? And my friends said that they were going to take a shot every time I said the word Bayesian. They know me. It's named after Bayes' theorem, which in turn is named after the Reverend Thomas Bayes, who lived in the 18th century. He wasn't well known in his time, but his theorem was later independently rediscovered by Pierre-Simon Laplace. But he was given proper credit. Skeptics, and it is another application of skepticism. This is the picture that's usually associated with Thomas Bayes. It's not him, we don't think, because he's not dressed in appropriate clothing for the time period in which he lived. So they think that somehow it was just a picture included with a text, and it got associated with him. But if you see this picture, this is the symbol for Thomas Bayes, even if that's not what he actually looked like. But Bayes' theorem is a theorem in probability theory. And the theorem itself is not controversial. There are controversial issues around Bayesian reasoning. Not so much Bayesian reasoning, but in any theory where you're applying probabilities, the question is, what does this probability mean? And what assumptions have you made? And that's where things can get controversial. But the theorem itself, within a well-defined problem, is not controversial. And what the theorem tells us is how we should update our beliefs in our theories, our confidence in our theories, given new evidence. And I didn't know about this until about 15 years ago. And I'm passionate about critical thinking and reasoning. And when I discovered this, my mind was blown. I'm like, there's a formula that tells you how you should update your confidence in a theory, given evidence? How did I not know this? How did my education system fail me? And it's just, whenever we talk about rationality, I always ask people, who was your rationality teacher in high school? Well, you didn't have one, right? Because we don't take it seriously, we don't teach it. So even today, the teachers don't know this for the most part. So what does Bayesian reasoning do? Well, the idea is that if you have competing explanations, we could consider theory B for the time being to be not A, right? So let's say theory A and theory B could be, let's say geocentrism and heliocentrism could be an example of two theories. And if you start out your inquiry not knowing which of these theories is more correct, then these theories are hypotheses. So in Bayesian reasoning, probability is associated with degree of confidence. And so the difference in the Bayesian mindset, the difference between a hypothesis and a fact is just how confident you are. That's it. That's the only difference. So a theory is a fact, let's say, and the line between fact and hypothesis, right, or fact and truth, whatever you want to call it, it depends on the context and it depends on sort of convention, but it's going to be some high number. There's going to be some number where you say no, it's a fact that this happened. Sort of implicitly, there's a degree of confidence that you have in that. That's why you call it a fact. So if I start out with two theories and I don't know which one is true, how am I going to figure out? How am I going to know which theory is true? Well, I'm going to know it because, in general, two theories will make different predictions about the world. So in this case, I'm imagining that there's a certain kind of test or some kind of evidence E And these theories predict evidence E with different percentages, right? So there's a 15% chance of seeing this evidence E in theory A, but only a 5% chance of seeing this evidence in theory B. So if I then go into the lab, would perform some test, and observe E, it's like I've created this sort of observation filter. And not every world that I could imagine passes by this filter. Only the two pieces that predicted E pass through. And the piece of theory A that passes through is 3 times larger than the piece of theory B that predicts evidence E. And so after basically the proportions of those bars below become my new updated inference, and that's how I've increased my confidence in theory A. So
I don't know, you're saying some predictions are consistent with multiple theories.
Yes. So this is another problem with a lot of science education. The most famous experiments are often experiments where it's like, oh, obviously theory A is correct and theory B, the probability of that is 0, we're done. But that's not how science usually works. Usually, both theories are compatible with the data in some way, even if it's just compatible in terms of the experiment was done wrong. Right? Both theories can account for the data. The question is, like, to what degree do they account for the data? So, in the language of Bayesian reasoning, the 50-50 that you started with was the prior, it was prior to the observation. And then the 75-25 that you ended up at is your posterior probability. So if we do another experiment, what's going to happen is the posterior from this observation is going to become the prior for the next observation. So it's iterative. So if I did another experiment, and then again, let's say did the same test, let's say I'm doing a test for a disease, I perform the test once, and now I'm more confident that the patient has the disease. Well, if I perform the test again, and again, they get the same result, then I'll become even more convinced of this. So I'm going to give a delicious example here. Imagine that I've just returned from vacation, and I was running low on cheese before I left, and I can't remember if I stocked up or not. So I really have no idea if I have cheese in my fridge or not. Right? It's 50-50. So what I can do, of course, is I could just glance in the fridge and see if I have some cheese. Well, the two theories, we have cheese and we do not have cheese, they're both consistent with me seeing cheese in the fridge, right? Maybe the package containing the cheese resembles a package containing tofu or something, and so I mistake the tofu for the cheese. But obviously we think that's probably less likely. Because if I have cheese and I look in the fridge and I see cheese, that's probably the most likely scenario. So I play the same game that I played before, and of course the biggest contributor here that passes through this filter is the obvious cheese, like cheese, we really do have cheese and I saw the cheese. That's the best explanation, but it's still possible I made a mistake, right? But bottom line is, the ratio of these two bars gives me my new updated probability, my new confidence level that I have cheese. So again, round one, that was my prior, was 50-50, and now I'm 90% confident that I have cheese, right? But maybe I'm really insecure about my cheese situation, and so I want to glance again in the fridge and just double check that I have some cheese. The same thing, I can apply this again, and again, the ratios of these predictions in each case are the same, but because this bar was larger, because my prior in round two was larger, it makes this bar larger, and that's how confidence in our theories grows, right? So what happens with Bayesian reasoning, it's a common sense, right? You keep, like just when you perform some mathematical operation, if I give you two 10-digit numbers to add together, and you add them up, what will you probably do after that? If it's important, you'll do it again. So Bayesians, by the way, people who are hardcore Bayesians like myself, we don't regard mathematics as certainty. We regard it as experiment. And this is how I became a Bayesian. I met someone, and I was just like, yeah, well, mathematical claims are certain, though, right? And he's like, no, you could have done the calculation wrong. But I'm like, Pythagorean theorem has been calculated millions of times, and we've used computers to do it. He's like, but you could have made a mistake. And it's like, it doesn't matter how small the probability is, you could have made a mistake. And 2 days later, I was a Bayesian. So rational confidence accumulates over these experiments. You know, if I've round to, obviously I was really insecure about whether I had cheese because I checked 10 times. So if I've checked 10 times, I'm really confident I have some cheese. And my friend comes over and I'm like, yeah, get some cheese from the fridge. And they're like, hey, I glanced in the fridge and there was no cheese. That's an extraordinary claim. It's an extraordinary claim because the prior probability for the theory that there's no cheese in the fridge is very small. That's what makes a claim extraordinary. Now, technically though, this data is no less reliable than my data, right? All the data that I used throughout those 10 rounds of checking the cheese, this is another round. But this time, because it's data that tends to support the we don't have cheese theory. If this were round one and the priors were 50-50, then I would be pretty confident that there was no cheese. But in this case, what is happening is when they say that the no cheese theory is now such a small sliver to begin with, that the part of it that passes through is also slim. So even though the no cheese theory predicts a 90% chance that you will see no cheese in the fridge, and the we have cheese theory predicts only a small percentage of probability that you won't see the cheese when it's really there, this bar is still larger. In other words, the size of this prior probability has an influence on what you see in the next stage. And so that one glance in the fridge where the person says, I didn't see any cheese, is not enough rationally to convince you that you don't have cheese, because you have so much evidence to the contrary. So, extraordinary evidence, right, does not constitute extraordinary evidence, because it's not enough to change your confidence and shift the confidence over to the we don't have cheese theory. Now, there could be different kinds of experiments you could do. Maybe there's an ultra-reliable cheese detector you could use in the fridge, or something that might reveal the truth. But if you're just using the same kind of evidence, you need to compile a lot of it in order to make progress and see to claim. So this is a sort of theoretical proof, a Bayesian proof, if you like, of the adage, extraordinary claims require extraordinary evidence.
I don't forget about this. How does the weighting, like really high quality technique, like you said, fall into this?
So when you have, so if I go back to my prediction, where the different theories to different degrees predict the same evidence, what will happen is if you have a really good test for something, then the positive rate here. So for example, with the classic Bayesian example is how to evaluate a mammogram test. And in the usual examples that they give you, they say like, if you have breast cancer, then the test will is 95% likely to show you that you have breast cancer. But if you do not have breast cancer, then it's going to give you, let's say, a 3% chance that you get a positive anyway. So then what this would be like 95%, 3%. So you have a very good test. The reason that if you do get a mammogram and you get a positive, that you still probably don't have breast cancer is that breast cancer is very rare. So in this group, this is the healthy, this is the disease scenario, but it's a very rare disease. So even 95% of this versus 5% of that the 95% of this small number gets drowned out by the 5% of this much larger number. So this is Bayes' theorem. I didn't want to put too much math in here, but you can almost see the same formula, right? This is the large bar, and this is the small bar. The small bar represents the alternative theory. So applying the formula is actually relatively easy. I'm just avoiding the math. But how might we apply this to something like the paranormal? So we tend to think of paranormal claims as being extraordinary claims. And the reason is that, as I've said, is that it must be that the prior for those things is small. But why is it small, right? Because depending on how things are framed, somebody could try and frame it as it's not unlikely at all. But it really is. And the reason it's unlikely is that we can imagine, if you didn't know anything about, let's say you came from an alternative reality, right? And you don't know, all you know, if you've been transformed, you've been placed into a new reality, and you know that either this reality is natural, like it's driven by relatively simple non-mental laws like chemistry and physics, or it's got ESP and ghosts and mentality is fundamental to it. If you didn't know which one of those worlds you were in, well, what kind of predictions would you make? What kind of world could you exist in? Well, we have a lot of fiction about fantasy and science fiction in which there are ESP and ghosts, and they're completely obvious, like in Ghostbusters, right? Everybody in the city sees the ghosts. Or the world of Dune, right? Nobody doubts that these people can fold space with their minds. It could be like dreams are super predictive, or we could live in the world of the X-Men, where people can use mental powers to do all sorts of things. There are lots of obvious ways these things could appear. But of course, it's possible that we do live in the ESP and ghost world, but we live in just that kind of ESP and ghost world that kind of looks like the normal world. But the prior on that is small. So the prior probability going into this might be 50%, like before you get any data, before you've looked at any evidence, the prior could be 50-50 that there are ghosts. But the probability, if you divide this theory into obvious and non-obvious, the non-obvious one is much smaller. And of course, what we observe is we don't see any ghosts. And every time we get a report of ghosts or ESP, and we do a test, and it's been resolved, it gets resolved in favor of naturalism. And so we've done this experiment numerous times, and so now the prior for this is tiny. And so claim, if somebody says they saw a ghost, or somebody says that I had some psychic experience, that evidence is no more powerful than any of the other thousands of pieces of evidence that we've had. It's not enough to overturn the theory.
So, does this mean that somebody may come into this with a prior that says, I'm 95% certain that ESP is real, right? So, their priors need to be amenable to the collection of evidence. And so, assuming that their reasoning process was good, then we should be able to see them change their mind. Is that right?
So the Bayesian reasoning is about the updating process. So assuming there's data available, it doesn't matter where your starting point is. You should be able to update and get to the truth. It becomes more difficult if you don't have a lot of data. Let's say you have one data point, like the existence of life on Earth is your data point, right? We don't have any other planets to go on. What could you infer from this? Then the conclusions can be more controversial. I wrote a book on this topic, basically naturalism versus omnipotent design. It's the same thing. It's the same Same idea. Basically, that if you have an all-powerful designer, it's not that they cannot create the world that we see. Obviously, by definition, they can. It's that they have an infinitely greater choice than naturalism does. So there are infinitely more designed worlds that they can create. And then it's not like they're worse in any way. They're in fact in many ways more beautiful than the worlds that evolution can create. It's not that you don't have to degrade evolution to, you don't have to say that evolution is worse. It's just that there are just an infinite number of alternatives. But if naturalism is true, then pretty much the only way to get life is evolution. So finding life even consistent with evolution is overwhelming evidence that we were not designed at any level. Like even a God that creates, configures the particles and fields in the early universe, knowing that humans specifically will evolve, it looks like, oh, I'm getting evolution and I'm getting design. That's ruled out. Just like any method of reasoning, Bayesian reasoning can be misused. In standard syllogistic logic, I can have all mammals are pink, elephants are mammals, therefore mammals are pink. So therefore elephants are pink, right? What's the problem? The problem is the premise is wrong, but this is a completely valid piece of logic. The same thing can occur with Bayesian reasoning. I think one of the things that scared a lot of skeptics away from Bayesian inference was a famous paper, or famous article by Timothy and Lydia McGrew that used a Bayesian argument to claim that Jesus was resurrected. And they made a lot of strange, dubious, and fallacious sort of assumptions to go into that, which I'm not going to go into in detail. We can talk about it later if you want to. But I think that, it's very human to go like, oh, these people use this weird reasoning method to get to a conclusion I don't like, that I think is wrong, therefore the method must be bad. But actually it was just the assumptions that they made. Another scenario, there's something called the simulation argument. It was created by Nick Bostrom, and it's sort of taken on a life of its own. Like the original argument is just a trilemma. It says, if it's easy to create simulations, and then easy to create simulations within simulations, then you're much more likely to find yourself being a simulation than a real person. And so that means you're living in a simulation. He wasn't proving that we do live in a simulation, but you will find people that will argue this, and they'll try and construct a Bayesian argument for that. But again, it comes down to the assumption. Does it really make sense to simulate life forms into existence? It's very expensive and probably very unethical as well. Then there's another danger is something called long-termism. It's not exactly Bayesian reasoning, but it's sort of a spin-off. So you remember when I said that Bayesians believe that for every proposition, there's a degree of confidence associated with that. Even mathematical statements, right? Certainty is useless because, like, how certain do you have to be that your trip to Mars is going to be safe? Well, it doesn't have to be any safer than you staying on Earth, right? Like, so certainty is not necessary. But the danger is that in this mindset, if you believe that there's a very small probability of something that has a very large payoff or a very large cost, you can weight that particularly high. And this, with long-termism, is the idea, for example, that, well, if AI could destroy civilization, that will end trillions of future lives. And so if we weigh those trillions of future lives against the paltry billions that live today, then clearly the most important thing I can do with my millions of dollars today is buy myself a new laptop to study AI. Again, it's not a fault with the method, but it's there are sort of ideas that in the cloud around Bayesianism that can throw us off course. So, conclusion, Bayesian epistemology, to me, like when I saw it, like I said, I was blown away. It's like a unified theory of rationality and skepticism. It's a powerful tool that can help you when aphorisms are vague or ambiguous, but like all reasoning methods, it can be abused. So, anyone has any questions?
We have a few minutes for questions.
Yeah, John.
So, getting to the abuse of it, it's sort of like, it seems like you use Bayesian reasoning to justify or rationalize the idea that if you tell a lie often enough and long enough, it eventually becomes true. That eventually there are enough people that believe in it, there's enough confidence in it, that becomes dominant.
You mean, so there are cases where humans do naturally think in Bayesian terms, right? Where the repetition, they use it as a model, right? But there are also cases where humans deviate from Bayesian inference, and many of those cases are basically cognitive biases, right? So when you explain things like stereotyping in Bayesian terms, and you spell out like what is the inference that they're doing, you can clearly see what the mistake is. So sometimes when I'm trying to understand the evidence around a topic, and maybe it's being framed weirdly, I'll write it out in Bayesian terms and try and identify like, where did this term come from? Like, what is the prior, and like, what is actually being predicted by each theory? So humans do have a tendency to be Bayesian in some contexts. Like there's evidence that when they're making judgments about like certain kinds of social behaviors, sometimes they can be very Bayesian. But there are also cases where we really strongly deviate from Bayesian inference.
Like a civilization that has a particular set of supernatural beliefs is propagated across generations. The Aztecs, the Egyptians, Christians, pick your mythology. That is widely believed, but that doesn't lend any credence to a Bayesian kind of analysis. Is that correct?
Right. So in the case when I was talking about naturalism versus omnipotent design, like one of the sort of pseudo heuristics that we often get in our head is like, well, these two theories, the theory that the world is natural and life just evolved, and the theory that there is a God that wanted to create a world in which life evolved but is still part of a plan. It seems like these two theories make exactly the same biological predictions, so how could you possibly tell them apart? And that was, and I didn't see it, and to me it seemed like, okay, yeah, that seems like a challenge, like how are we going to figure that out? But I always came away thinking, and I think the consensus among most atheists and Christians who care about science is that what Darwin did is he took the idea of the argument from design as it applies to biology off the table. He neutralized it. But it always felt to me like, well, it seems like it still doesn't fit as well with theism, design theism, as it does with naturalism. So why don't I plug it into Bayes' theorem? And what I realized when you do that is that in order to answer the question, how likely is it, you have to say, well, before we had any evidence, any biological evidence, what we have predicted life looked like. And if it was designed, there are, for example, you could create hyper-intelligent, semi-robotic frogs, titanium ducks, and it could be that the world's greatest expert on quantum field theory is some sort of rabbit that lives somewhere. There could be just like 12 hyper-intelligent rabbits on the entire planet and nothing else. They're all God-powered, right? what's happening is we weren't thinking about all of the alternatives that an all-powerful creator could create. We're not realizing that the prior probability for that scenario is really small. I think that some of us intuit it maybe a little bit. Like when you see the evidence for evolution, you do tend to get away from design theism. But I think a lot of people, if surveys are to be believed, most Christians actually want to accept evolution and design. And they're able to do that because they don't think about those priors. So to me, the value of Bayesian epistemology is that it allows you to, like, I think the heuristics are just incomplete. Like, we can make mistakes just by not thinking about, oh yeah, there are so many other, that's not what you would predict. Other questions?
Any other questions?
Just an observation. So, I mean, this works well for a person who is willing to accept that they may be wrong. But it will not be someone who is, like you said, the cognitive bias. This wouldn't be applicable to them because this just isn't the way they're thinking about that particular piece. Would that be a correct statement?
I mean, yes, but I guess does that apply to all sort of skeptical thinking? Like, I mean, this method it may be even more difficult for people to understand because it's a little bit more technical. But
Well, you said it was based upon quality evidence. I don't know if you use that word, but it's based upon whatever your observation is or whatever your conclusion is. It should be appropriate evidence that you would accept that to change your position. All I guess I'm saying is that for someone who is in a dogma situation, that won't matter. Doesn't matter what the end result is because their dogma will say that can't be right.
Are we talking about the confirmation bias, people who are seeking information that only prove their theory and will not open themselves to something else, which is essentially to what you're talking about?
so the Bayesian epistemology for like the Bayesianism is kind of the view, so that there's Bayes theorem, then there's Bayesian reasoning, then there's Bayesian epistemology, and then there's Bayesianism. And I'm all the way down on the Bayesianism thing. Bayesians like myself think that Bayesian inference is the same thing as rationality. And so if you say somebody is not going to update in a Bayesian fashion, that just means that they're not rational. And so, of course, they're not going to accept.
And we see that all the time.
Yeah.
Right.
I do think that we should teach rationality in schools, like even just basic conceptual differences, like the difference between epistemic rationality and instrumental rationality, right? So there's the rationality of knowing what's true given the evidence, and then there's the rationality of winning. How do I best satisfy my desires? And most of the time, those things go hand in hand, but not always, right? So somebody could say like, well, I know I'll be happier if I believe something that's not true. Or maybe I will be more successful if I have inaccurate beliefs about how good I am in this industry. I'll just have more confidence and I'll do better, but I'll have false beliefs. So that understanding those distinctions, and the distinction between deduction and induction, for example. Like in schools, we teach deduction, like mathematics in schools is almost entirely deductive, right? But induction, how do I update my confidence based on new evidence? You'd think like, well, that sounds like a science thing, right? But we don't really teach that in science either. So we kind of don't, we learn by example. It's like we come into school knowing how to learn by example, by watching other people, and then we don't improve on that skill in any formal way.